presentation that I'm going to show you, but in the paper that hopefully is going to be published shortly in Journal of Hydrology. We've submitted, we have to send in, I think we got moderate revision that we'll be submitting very shortly, so I'm hoping that shortly is going to be actually published. Right, now on to the actual subject matter of today. I'm going to talk about hydrological forecasting, and specifically I'm going to talk about ensemble prediction, given the need of or the wish to estimate uncertainties in the forecast. As you all know, ensemble prediction systems will yield an uncertainty estimate. Specifically, the research is going to be about how these predictive uncertainties can be reduced. And I'll go into that a bit further in a bit. The idea is that many of these hydrologic forecasting systems are forced by numerical weather prediction products to extend the lead time, if the required lead time is larger than the concentration time of the basin. However, many of these products are biased. They can be biased in the mean, they can be biased in the spread. And the problem for hydrologists is that these biases tend to propagate through the system into the actual streamflow forecasts. Now, there's a couple of solutions that you can apply to try and reduce these biases. And one of these solutions is statistical post-processing. Now, what is often done within the ensemble streamflow prediction systems is that statistical post-processing is applied to the streamflow forecast directly, if you like. That usually works pretty well, but what you could also do is you could apply the statistical post-processing to a single source of uncertainty. In this case, you could apply it to the numerical weather prediction products. In a hydrological forecasting system, if you're applying statistical post-processing to numerical weather products, we talk about pre-processing. This is very distinct from what the meteorologists say. They're always talking about post-processing, but for the hydrologists, it's also called pre-processing. Because it happens prior to the hydrologic model being run. And indeed, that is the topic of today's presentation. What we're looking into specifically is if you do apply statistical post-processing to, say, your precipitation and temperature forecasts, you're hoping that that's going to improve the quality of your streamflow forecast also. And the question is, is that indeed the case? And how, does the quality improvement in forcing ensembles propagate to the streamflow ensembles? So the research question that we posed for this research is, to what extent can the biases in streamflow forecasts be addressed through post-processing of the forcing ensembles? So again, through pre-processing, if you like. If you divide it up into a couple of sub-questions, then what you could do is you could try to evaluate to what extent the raw forcing ensembles are biased. So these are the forcing ensembles that we receive straightly from the Meteor Institute, in this case ECMWF. Then you can evaluate how these biases propagate to streamflow ensembles by doing, applying certain verification metrics. What we can then try to do is try and increase the quality of the forcing ensembles by applying post-processing, statistical post-processing to the precipitation and temperature ensembles. Again, we wrote these through a hydrologic model. This results in streamflow ensembles, and these again you can evaluate in terms of a couple of policy aspects. Today's presentation, like that was the introduction. The outline is I'll show you what materials and methods we use and applied in this research. I'll discuss some of the results with you. We've drawn some conclusions from that, and after some closing statements, maybe there's time for some questions. So in terms of research design, essentially it's very simple. We have two cases, or two principles really. We either take the raw forcing ensembles, route them through a hydrologic model to arrive at streamflow ensembles. These we verify using a number of metrics. The second case is we take the post-process forcing ensembles, we route these through a hydrologic model to arrive at streamflow ensembles and verify these, and then we compare the results between those two cases. We've done research using a study basin. The study basin in this case is the basin of River Rhine, which is located in Central Europe. I'm hoping you can see the pointer. Can you, Florian? Can you note if you can see my pointer? Yes, you can. So this is the Rhine basin, Switzerland here in the south. Some of the basin is located in France. Most of it is in Germany, and eventually it flows towards the Dutch border. And we have the point of outflow here at Lobit. It's not really the point of outflow, but for practical purposes, we take this to be the outlets at Lobit in the Netherlands. You'll see a couple of stars, and on the map, the yellow star is the outlet at Lobit. There are four main tributaries. We have the Mosel, the Neckar, the Main, and here the Swiss Rhine that'll come back in a second. And then you see approximately 40 small stars at the headwater base, at some of the headwater basins. Okay, these aren't really headwater basins in the sense that some of these could be relatively large, but these are the smallest entities in the hydrologic model that we used. I think the largest of these is approximately 2,000 square kilometers large. And if you compare it with the outlet at Lobit, that's approximately 170,000 square kilometers large. So it's a considerably sized basin for mainland Europe anyway. In the project we used, sorry, I'm going one step back. We used a hydrologic model, which is a HPV model, a conceptual model. It runs at a daily time step, so every time step takes 1 day. There's some hydrologic routing involved within the model, but we did not couple it to a hydrodynamic model, so it's hydrologic modeling only, if you like. In terms of data, in terms of the forecast data, we use the ECMWF reforecast set. This is a set of data. I think every week, every Thursday at ECMWF, they retrospectively produce forecasts for the past 18 years, 17 or 18 years. They do that once every week, using initial conditions from that time. So today is March 27th, suppose this were Thursday, and the retrospective forecast would be produced for March 27th, 2012, 2011, and so forth. These are 5-member ensembles. For production, they use the operational forecast model, so it's a fairly homogeneous set. It evolves with the evolution of the operational product at ECMWF. All in all, we had approximately 3,000 forecasts available. In terms of observations of precipitation and temperature, we used the two sets of observations that are available. One of them is the EOPS set that was produced by the Dutch Met Office, which is a set of daily average temperature values at a fairly high resolution grid. The other is a product that's derived from the product you see here on the left, which is a precipitation grid. Again, we're using observed daily precipitation. And both sets, the precipitation set is the CHR08 set, which was produced as part of a research project here a couple of years ago. They both go back to the 1950s or 1960s, so it's a pretty extensive data set, if you like. In addition to that, we're using streamflow observations that are available at the hour scale and that we've aggregated to daily mean streamflow observations. So that's the data that we've used in the project, in the research project. As I said, we're talking about post-processing. Here I've called it bias correction, but it's the same thing really. We've used a couple of techniques. For temperature, we use the quantile-to-quantile transform, which is an unconditional technique. Probably, most of you would be familiar with the technique. It's unconditional in the sense that you apply one transformation to a full data set without looking at the actual extent of the precipitation information to a high observed precipitation predicted precipitation value as you would to a low predicted precipitation value. In addition, for temperature, we've used linear Gaussian regression, which is a fairly standard method of post-processing temperature forecasts. For precipitation, obviously, precipitation forecast would be non-Gaussian distributed, so we couldn't use the Gaussian regression. We had to resort to logistic regression, which again is a fairly standard technique in this case, and we also apply the quantile-to-quantile transforms. So what we have, I'm going to go one step back, is for temperature and precipitation, we have an unconditional technique, which is the quantile-to-quantile transform, and we have the conditional techniques, which are the Gaussian regression and the logistic regression. Now, in terms of the latter, in terms of the conditional techniques, the principle is similar for both. What we're trying to do is we have a predictance here called y, and we have a set of potential predictors here termed x. We're just assuming that the predictant y is unbiased. Obviously, there's going to be some measurement uncertainty, but we're just going to ignore that for the moment. What we're aiming to do is by post-processing, is to arrive at a bias-corrected or post-processed forecast, which is a distribution of the predictant conditional on a predictor or on multiple predictors. So we arrive at a probability distribution, which is a cumulative distribution, basically. In our case, we've not used all of the ensemble. You could conceivably use all of the ensemble members as predictors. In our case, for the conditional techniques, we've used the ensemble mean as a single predictor. We do this for each lead time and each location separately, and after the bias correction, we apply the Shatley shuffle to maintain the spatial and temporal patterns. Why is this important? This is important because in hydrology, the streamflow forecasts are highly dependent. They more or less constitute the integration over time and over space. So if you mess up the spatial and temporal patterns, you're going to get really strange hydrologic forecasts. That's not what you want. And because you apply the post-processing separately for each lead time, each location, after the post-processing, you need to try and restore some of these patterns to get some sensible traces. Well, we have a couple of techniques then, a couple of cases if you like. We have the uncorrected temperature and precipitation ensembles, which are termed raw and roll in this presentation. We have the unconditional quantile-to-quantile transforms, and we have the conditional techniques, which consists of the linear Gaussian regression and the logistic regression. Okay, so we have three cases that we'll compare to one another. We verified all of the ensembles in terms of, it says here verification against simulations. That's only true for the stream flows, obviously. Temperature and precipitation is verified against observations. I'm going to show you a couple of metrics. Some of these are scale scores. The scale scores shown are relative to sample climatology. Okay, that's important to keep in mind. All the metrics that I'm going to show you will be expressed as a function of the climatological probability of exceedance of the observation, and I'm going to explain it to you in a second. I'm going to show you how that works, but essentially what we're doing is we're evaluating, say, a full sample, taking all approximately 3,000 verification pairs, a pair being a combination of a forecast and an observation. But what you can also do is you can take a subsample. Say if you're interested in high precipitation amounts or in high temperatures or in high streamflow values, you can take, say, the top 10% of observations that are part of the pairs and then only verify in terms of that subsample. Now we've done that, and that gives you some idea of whether or not the quality of the ensembles is conditional on the height or on the observed value in terms of, is it a large observation or a small observation. But I'll come back to that in a second. We've used a couple of metrics. They're all fairly standard metrics, fairly often used in this type of study. Bear with me. This always happens, of course. We've used the relative mean error. We've used the continuous rank probability scale score, the CRPSS. We've used the relative operating characteristics scale score. And in addition, not listed here, but I will show you some results in terms of the Brier scale score. Each of these metrics were computed using the ensemble verification system that was developed at NWS. Now, the graphs that I'm going to show you are all similar to this graph. What you see here on the horizontal is the value of the paired observation. So this is the observation that's part of the pair, labeled with the climatological probability of non-exceedance. So at t equals 0, we have the full unconditional sample, basically the full 3,000 odd verification pairs. And if, for example, you look at a higher value of p, say close to 1, that means that we're looking at a subsample, and in this case, they would be the pairs with the top 1% of observations. Okay. So that's the horizontal axis of this plot. And all of the plots I'm going to show you have the metric on the vertical, ranging from best at the top to worst at the bottom. And for scale scores, we have a baseline where the scale equals 0, and that's indicated by the gray line. And we're going to get back to this plot quite a bit. So here are some of the first results which pertain to temperature. These are temperature forecasts at a number of lead times. So we look at 24 hours ahead, 120 hours ahead, and 240 hours ahead, 1, 5, and 10 days ahead. These are the different metrics: the relative mean error, the continuous rank probability scale score, the Brier scale score, and the relative operating characteristic score. I hope you can see that there are a couple of colors used. Now, the red lines are the lines for the uncorrected, say the raw forecasts. The blue lines, and here it's hidden behind the green line, but the blue lines, you can see them here, are the unconditional quantile-to-quantile transformed. So the post-processed forecasts, with the green line being a Gaussian regression, linear regression, and post-processed forecasts. Now you also see thick lines, solid lines, and you see dashed lines. This graph pertains to 134 basins. So we have 134 results for each of the metrics, each of the lead time, and each of the value of p. We've tried to capture the distribution by showing a median, which is the solid line, and by showing a dashed line, which is the 10th, which are the 10th and the 90th quantiles or percentiles, if you like. So that gives you some sense of the uncertainty across multiple locations. Okay. So they're pretty complicated graphs. Don't hesitate to ask me any questions afterwards if you think that they need some additional explanation. So what we look at, these are temperature ensemble forecasts. If you take a very global view, you notice a couple of things. One is that the quality of the forecasts tend to reduce with increasing lead time, which is something that you'd expect beforehand. And indeed, this is shown in the results. So going from left to right, in between the plots, from the left column to the right column, basically always you see a decrease in quality. One other thing you notice is that within a single plot, you see that the quality of these forecasts is conditional on the observation, meaning that if you look at the left, I'm looking at the uppermost left, the plot on the left and on the top. If you look at the value of p is 0, you get better quality than if you look at the more extreme values only, at higher values of the non-exceedance probability. Okay, that's something that we would have expected beforehand, and that's something that indeed we see in all of the results. Now there's a couple of interesting things. I'm going to remind you that the red lines are the raw forecast, uncorrected, and the green and the blue lines are the post-processed forecasts. What you see is that in terms of relative mean error, there's quite a distinct improvement if you move from uncorrected to post-process temperature ensembles. You see, however, that at low values of P, the improvement is higher than at high values of P. And you see that, you know, in for all of the lead times, basically. Also, if you look at the continuous rank probability scale score, you see that if we move from the raw to the unconditional to the conditional post-processing techniques, that we get additional improvements in forecast quality. The same is true for the Brier scale score, and the same is true for the relative operating characteristic score. Meaning that in terms of temperature forecasts, the unconditional quantile-to-quantile transform forecasts are an improvement over the uncorrected forecasts, and in turn, the using the Gaussian regression constitutes an improvement over the unconditional techniques. Now we're moving to precipitation. Now the message gets a little bit more complicated. What we see here is that we have precipitation for 134 basins. Again, we have the 3 different lead times. We have the same scores that we saw just now in case of temperature. What we see here is that if you move from the red line, which is the uncorrected forecast, to the quantile-to-quantile transform forecast, in some cases there's an improvement, and in some cases at the higher values of the observation, there's actually not an improvement. We're actually reducing forecast quality. We also see that in terms of the logistic regression, that at the lower end of the distribution, that there's an increase in relative mean error, a decrease from a positive value going to 0. But if you go further out, then you'll see that the relative mean error is higher in the absolute sense than the other two forecasts, which is something that is a little bit unexpected maybe. Now, I would like to remind you that relative mean error could be a natural property of ensemble forecasts, but still you'd hope that, using a conditional technique, that the error would be reduced, which is not actually the case here. However, again, I'd like to remind you that if you look at the full sample, we do indeed have an improvement over the raw forecasts. So not all is lost, thankfully. We also see that with increasing lead time, the effect tends to become smaller. Okay, so for the first few lead times, you're well able to pick up some additional signal in the raw forecast, but with increasing lead time, this becomes more difficult, and the lines are closer to one another in the quality metrics plots. You see similar patterns for the continuous rank probability scale score, similar in the sense that unconditionally you see an improvement for the conditional techniques, for the most complicated techniques if you like. But if you move further up to the more extreme values, then the results of the post-processing using logistic regression are actually worse than those for the raw ensembles or for the quantile-to-quantile mapped ensembles. We do see, in terms of Brier scale score, that there's nearly always an increase in quality if you move from the raw forecast to a quantile-to-quantile mapped forecast to a logistic regression process forecast. And the same is true for the relative operating score for most of the lead times, but not necessarily at the highest lead time. So as I said, it's a little bit of a mixed message. If you try to post-process precipitation, in some cases you improve the quality, but it's fairly often it's a bit of a balance where you improve on the one quality aspect and you reduce on another aspect. I'm just going to skip this one here. Here we're going to look at the decomposition of the Brier scale score. And as I showed you earlier, again, this is precipitation for 134 basins. We have seen an increase in Brier scale score for most of the lead times. Basically, for all of the lead times, you see that the logistic regression outperforms the raw and the unconditionally transformed forecast. And then if we try to see why that is, these are decompositions. This is the reliability decomposition, and this is the resolution decomposition. It's fairly obvious to see that in all cases we have a higher Brier scale score because the reliability component has improved. So basically, by applying the post-processing technique, we've improved on reliability in terms of the Brier scale score. However, if you look at the type 2 conditional bias, which is a bias, it's a reliability conditional on the observation, you see that logistic regression does worse than the other techniques. So that's an interesting finding. If you look at Brier scale score, you do improve on reliability, but you do not improve in type 2 relative bias. So that's somewhat disappointing, maybe. You do make up for that by getting a sharper forecast, whatever that's for. So just, summarizing, we were able to improve the temperature forecast pretty much, along all lines. In terms of precipitation forecast, that proved to be a lot more difficult. So now what we're going to do is we're going to see if the quality improvements in precipitation and temperature, if they propagate to streamflow ensembles. Now what we're doing is I'm going to show you a couple of similar plots that you've seen a second ago, but for streamflow we've divided up the results in 3 different spatial scales, 3 levels if you like. I'm going to show you results for the basin at low bits, for the full basin. I'm going to show you results for the 4 main tributaries, which are still reasonably sized basins, and I'm going to show you results for the, I think it's 43 headwater basins. Why have we split it up? We've done that because we expect there to be some dependency on the spatial scale. So we'll come back to if indeed that's what we see. So again, here we have a couple of verification metrics for the streamflow ensembles. These are the similar metrics that we've seen before: relative mean error, continuous rank probability scale score, Brier scale score, and the relative operating characteristic, using the same lead times. And here we see what's striking here. We see similar patterns in the sense that with increasing lead time, we see a reduction of forecast quality. And also with increasing value of the observation, we see a reduction in quality. So this is, if I use different words, for the higher observed stream flows, our forecasts do less well than if you look at the full sample. It's more difficult to correctly predict an extreme value than it is to predict a non-extreme value. Okay. We also see that at a 24-hour lead time, the forecasts are near perfect. Okay, this is of course a result of the fact that we're verifying against simulations, and because we're verifying against simulations, the initial conditions will be perfect. So these plots, you have to keep in mind if you look at these plots that initial condition uncertainty is absent. Just know there we've omitted it from the equation, basically, purposely so, because we want to isolate the effects of post-processing of temperature and precipitation ensembles. So these are results for the 43 headwater basins, the smallest spatial scale that we look at, and I'm just going to draw your attention to the 120 hours for the simple fact that even for the smaller basins, it's very difficult to see a difference in forecast quality. And again, this is because even though they're the smallest basins that we looked at, they're still reasonably sized in scale. If we look at the 120 hours, that's the 5-day ahead forecast, then what we see is that for the low values of P, there's almost no difference in streamflow quality. However, if we look at the higher observed discharges, we see that red were the uncorrected forecasts, that there's some improvement in quality when using the quantile-to-quantile mapping in terms of relative mean error. But if we look at the conditional techniques, remember the Gaussian regression and the logistic regression, there's actually a decrease in forecast quality. Let me see. That's not actually true for some of the other metrics. You can see here that in terms of CRPSS and BSS, the quality metrics are very similar to one another. It's a slightly different image if you look at the relative operating characteristic, where you see that indeed when moving from raw to unconditional to conditional post-processing techniques, that constitutes a quality improvement, but not necessarily for all of the metrics used. Again, if we look at the decomposition of the Brier scale score, we've seen just now that if you look at the scale score as a whole, the scales are very similar. However, we do notice that if you look at the decomposition, that there's a little bit of a trade-off between reliability and resolution. Where in some cases you'll improve on reliability, but the quality expressed as the resolution will actually be decreased. So that's an interesting thing that we need to keep in mind. I am actually going to skip some of these. This is a figure with a wrong caption. The results I showed you just now pertain to the 43 headwater basins. What I'm going to show you now is some results for the 4 tributaries. So this is a different spatial scale. What you see at the larger basin, and this is something that should be unsurprising, is that at the 24 lead time, there's barely, the forecast quality is near perfect. Obviously, this has to do again with the initial conditions, and we'll see later on that at the outlet at low bit that effect is even stronger. Now, what we see here is we see similar patterns where for the low values of the observation, or the low to intermediate values of the observation, forecast quality is reasonably unchanged when applying post-processing to the forcings. Only at the higher levels of observations do we see a difference. And in this case, we see that again, the relative mean error has been increased in absolute sense when moving to the conditional techniques. And the same is true for some of the other metrics that we see here. And the last plots that I want to show you is for the Rhine outlet at low bit. And again, this is, again, a larger basin. Forecast quality at the lower lead times is near perfect, and only at the longer lead times do we see an effect of the post-processing of forcings. What we see here is similar to the smaller basins in the sense that in terms of relative mean error, there's not actually an improvement, not if you use the conditional techniques, but there will be an improvement if you look at the relative operating characteristic score. So I suppose the message is it really depends on what metric you're interested in, what's important for you for the decision that's made based on a forecast. That should be taken into account when you decide to use these post-processing methods. Now just to go back, we've seen that post-processing of forcing adds some scale to the, this says Streamflow forecast, but I mean to the forecast of temperature and precipitation. However, this increase in quality does not proportionally propagate to the Streamflow ensembles. Why is that? Well, there's a couple of things we can think of. One would be the strong nonlinearities, that are associated with hydrology. The other is the presence of storages. The Rhine, is known to have a reasonably sized snowpack. It's a relatively large basin with relatively large groundwater storages. There's some man-made reservoirs even, and obviously, these would hinder the propagation of forecast quality from forcings to stream flows. Another possible source of the absence of quality improvement in the streamflow forecast could be that well, we've used the Shaki shuffle to try and restore some of the space-time patterns. This may have been inadequate. But to be honest, this is something that we need to look into, as we didn't specifically try to isolate that in this research. If I put this in some perspective, then I'd like to note that these results are largely in line with the results obtained in similar studies. There are two studies that I know of, and pretty much the conclusions drawn in those studies are fairly similar. As well, it is possible to improve on your precipitation and temperature forecast. It's very difficult to improve your streamflow forecast by doing the pre-processing. What does that mean for operational streamflow processing? Well, you may want to consider post-processing rather than pre-processing or only pre-processing. There's one question there's more questions, but there's one that I'd like to mention. Again, I'd like to remind you that in this case, we've verified against streamflow simulations. We need to have a close look at what happens if we verify against observations rather than simulations. We've done that, very tentatively, and we have noticed that then the initial condition uncertainty becomes pretty dominant in terms of the sources of uncertainty, especially for the shorter lead times, obviously. So the question is, given the fact that the effects of pre-processing are muted if you look at streamflow forecast quality, they may be fully absent. They may be, I'm not saying they may be fully absent if you verify against observations rather than simulations. But this is something that we need to look into at a later stage. Then before I take questions, if any, I'd like to draw your attention to the following. In a couple of weeks, there's going to be the annual assembly, the General Assembly of the European Geosciences Union. If you're interested in pre-processing, post-processing, streamflow forecasting in general, there are going to be some interesting sessions. For example, there's a session by Bob Moore and others on uncertainty estimation and post-processing. Then there's a session of Florian and others and Charles John on ensemble forecasting. And there's one that actually fell off the page, and that's on hydrology and decision making. All of these sessions on hydrological forecasting take place on the Thursday and the Friday. So it'd be nice if we could see some of you there and meet you there. Then one last remark. This presentation was one in a series of webinars organized by HEPEX. The next presentation is going to be given by Will Potsy. It's going to be on the global footprint of droughts and on drought forecasting. This presentation will be given on Friday, April 19th. That's after ETU at 10:30 a.m. in the morning. So that's the next general presentation. And while we're at it, if any of you would like to give a presentation at some point of time, please contact Florian or myself, because there's some room for additional presentations in the schedule. And with that, ladies and gentlemen, I'd like to conclude my presentation, and I think this will be a good time for questions if there are any. Thank you very much.
Thank you very much, Jan. It was a very interesting presentation. So if you have any questions, you just have to make yourself unmute, obviously, before you can do so. I think Frederick had one, which has to be next to me.
Sorry, hello, Jan. Can you hear me?
Yes, hi Frederick, I can.
Oh, thank you. Very interesting presentation. I was just curious in the beginning how you set up your model to be to the routing with the HPV model. I missed that part of your presentation.
Sorry, which part did you miss?
How you set up the routing between the watersheds for the Rhine basin.
There is a hydrologic routing component built into the HPV model. That's
okay.
what we use. So there is routing in the model, but it's not what we usually do in the real operational system. Like the system that I use is a derivative of that. It's a hydrodynamic model that's linked to the HPV model. But in this case, we use the built-in headwater routing only.
So the water just basically passes from watershed to watershed. There's no routing in the river there.
Well, there's routing, but it's not hydrodynamic routing.
Okay. Yeah. All right. Thank you.
Any other questions?
Yes, Jan, thanks for. Do you hear me, guys?
Yes, Jan, I can hear you.
Good. I have a question about actually your last point about what to expect when to verify against observations, streamflow observations. Because I couldn't quite hear whether you expect it to improve or to get, let's say, to increase or to get even less the impact of pre-processing.
I think that if you verify against observations, the quality improvement is going to be even more muted. So it's going to be less noticeable. For the simple fact that what we've done in the study is we verified against simulations so that we could isolate the effects of pre-processing. If you no longer isolate the facts, some other sources of uncertainty are going to come into play, and the relatively modest increase in quality is going to be even smaller.
Yeah. Okay. I think indeed the same. So I wanted to check that idea. In that sense, it's still interesting indeed to discuss more or to research more. But indeed, even with the effect isolated on the input, which is the precipitation input, why the effect is muted.
Sure.
There, or how actually? Yeah.
Yeah.
That's an open question.
I agree. That's an open question for the moment. And as I said, we have some leads. We think it could be due, like it could be due to the fact that water is stored. So simply, you could have a perfect precipitation forecast, but if that precipitation does not translate into stream flow, then you're not going to be able to measure that quality in terms of stream flow simply because the water has not reached, your channels yet. And these storages could be in the groundwater pack, in a snowpack, in man-made reservoirs, name it. And I suppose that the basin we looked at is still relatively large, and maybe, if we want to look into that in more detail, we need to look at smaller basins, as the next step, if you like. So that's, that would give us some lead for further research, but that's still open.
Okay.
Would there be any other questions by anybody?
Okay, if there's no other questions, I'm sure you can email Jan, and he put his email onto the screen in case you have any others. Thank you very much for attending. Thank you very much, Jan, for giving this presentation. Again, I want to reiterate, if anybody of you want to volunteer to give a presentation, that would be great. I think we're all interested. Participants numbers are going up and up, so that's quite nice to see. Okay, then I want to conclude, and I hope I see you next time. It's a bit early in the month, I'm sorry for that, to a presentation by Will, who's going to be here at ECMWF, and therefore I decided to make it to a HEPEX seminar at the same time. Okay, thank you very much.
Thanks.
Bye-bye.